test how PCR primers perform in silico. So at present we have quite a high reliance on PCR as a diagnostic test. So it's used in a lot of diagnostic laboratories around the world, and the current two established tests that we use are generally that does not do what I thought it did, are the Callahan PCR, which targets the 3D region, and the Reed PCR, which targets the 5' UTR. And these are very conserved regions within the foot and mouth genome. And we use these PCRs because they're highly sensitive, they can be used on a large amount of different sample types, and they're very high throughput comparatively to other techniques. And this high reliance now means that we quite often use PCR as an emergency response to test for samples. So, for example, in 2007, during the UK foot and mouth outbreak, of over 3,000 samples that were submitted, 99.1% of these were tested by real-time PCR, and only 21.8% were tested by virus isolation, which is considered the gold standard. And this is for a number of reasons. So firstly, PCR can be used on a high amount of sample types, and also it's very rapid. However, in doing this, we're making an assumption that the PCR primers and probes that we use are still fit for purpose, although they haven't actually been re-evaluated since they were initially made. So why haven't they been re-evaluated? Firstly, time and money. So it takes a lot of time to re-evaluate PCR primers and probes on new sample types. And just looking at the numbers of samples that originally PCR assays have been validated on, it's actually difficult for many laboratories to get hold of this number of samples. So therefore, there's not been re-evaluation of these tests since they've been created. However, this isn't just a problem for existing tests, this is also a problem for development of new assays. So recently there's been a push to create a number of serotype-specific assays because they're more informative than the pan-specific in terms of serotype. And these generally are located within VP1 or the capsid region, which are more varied regions. So again, just looking at these tests, they're validated on a large number of samples, which can be difficult to get hold of. So, for example, Kasia, her assay, 27 of these samples even had to be validated in East Africa to just get hold of the samples. But it's not just 356 samples, it's 356 samples done in duplicate on about 5 different primer sets. So it results in about 2,500 assays having to be performed just to validate these tests. But why do we need to re-evaluate? So in PCR, the CT value is not only reflective of the amount of virus in a sample, it's also reflective of the amount of mismatches between the PCR primers and the templates. So if we have a poor CT value, we can't be 100% sure if there's a low amount of virus in the sample, or actually if the assay is just performing badly due to the high numbers of mismatches between the primers and the template. And this is more of a problem when targeting highly variable regions where it's very rare that your PCR primers and probes are actually going to match all your serotypes you're trying to detect 100%. And this is problematic when considering samples such as probang in carrier animals or serum at the start and beginning of viremia, because you're going to have a very high CT value anyway. If we have a large amount of mismatches between the primers and the templates, you can easily call false negative samples as it pushes the assay over the threshold into a negative. So this leads to our solution, and we were going to try and design an in silico program to quantitatively predict how PCR primers and probes would perform without the need for having to do all this laboratory evaluation. So to do this, we had 3 aims. Firstly, to investigate the influence of mismatches on PCR. So there's already quite a lot of data out there on how this actually affects PCR. However, it's limited in terms of looking at different enzyme kits. It's limited in terms of looking at different amounts of templates. So most papers pick one amount of starting templates and do all their analysis based on that. And based on the data that we got, we were hoping to design a bioinformatics program to therefore predict how primers and probes would react, and then validate this program using naturally occurring mutations for foot and mouth disease. So to do this, we started looking at PCR. So we omitted RT for this stage, and we based all our evaluation on the Callahan 3D region, just because it's a very well-known assay. So I designed 90 different linear DNA constructs around this region, and these were made to vary in the primer and probe binding regions. So there were differences made at the 3' end, at the 5' end, with different mismatches made. And we had a maximum of 6 base matches designed per primer. The PCRs were then all performed as they would be in a diagnostic laboratory, with various different starting templates, and all these mismatches were compared back to a perfectly matching template. So, firstly, we looked at how different enzyme kits coped with mismatches differently. So we compared the superscript 3 kit, obviously omitting the RT stage, because this is the kit that's used in diagnostic laboratories, and compared it to a second TAC-based polymerase kit. So just to quickly explain the graph, each of these points here represents a different DNA construct, so one that we designed to have various mismatches in it. And the axes represent how much those mismatches affected the CT value, so the superscript 3 kit and the Excite kit. And we did actually find a very strong linear relationship between the 2 kits, so they both reacted to the mismatches similarly. However, the more mismatches, the actually slightly harder this was to predict, so there was more of a range in terms of how the mismatches affected PCR at this end. But we took both data sets forward for both enzymes for our analysis. So we then looked at how each mismatch affected the CT value of a PCR. So we used a linear model at this stage to combine all the data from both enzymes and all starting templates to basically look at the average effect of how a mismatch in a primer or probe would affect the CT of a reaction. So we split up our mismatches into 2 types, transition and transversion. Just for simplicity, transition mismatches were the mismatches that resulted in the smaller conformational change between your primer and your templates. The transversion resulted in your primer and template being less able to bind. There was a large conformational change. So just looking at the graph on the left, these were the 4 nucleotides nearest the polymerase binding site, so at the 3' end of a primer. And we found that just by having one transversion mismatch, just one single mismatch in your primer at the very 3' end, resulted in a change of CT of about 6. So to put this in perspective, that's like underestimating the viral load in your sample by 2 logs, which is huge, and it could easily push a positive sample into a negative. And for a transition mismatch, it resulted in a change of CT of 3. So again, this is like underestimating the amount of virus in your sample by a log. So the mismatches at the 3' end had the most pronounced effect, which we know. But we found we could tolerate a total of 2 mismatches at this 3' end before the PCR reaction was knocked out completely. So if 2 of these were present, you wouldn't even get a PCR value. And a minimum of 82% match was required across the entire primer and probe regions in order to get any amplification at all. So again, otherwise your PCR would be completely knocked out. Because we looked at various different starting templates, we were also able to look at the PCR efficiency of a reaction. So we know that the CT changed when we added a number of mismatches, but we wanted to also see if the efficiency of a reaction would change with these mismatches. And we used linear regression in order to do this. So we found actually that although the CT changed, the efficiency of the reaction did not. So the gradients of the lines for each of the constructs were very similar. And we believe this is the fact that the mismatches affect the starting rounds of PCR, not the finishing rounds. So once a primer has bound to your template and extension occurs, the resulting amplicon is a perfect match to your primers because it contains the primers. And therefore, it affected, the CT and not the efficiency of a reaction. However, we then had to actually do something with this data and design our program. So this is, don't worry about the data in the table. However, this is just the output of the linear model we got. So basically, we had a number of different variables, which were the different mismatches in the primer or the probe, or the percentage change in the primer or the probe, and each of these gave us a change in CT of the reaction. So for a nucleotide 1, we got an increase in CT by 3. And it was this data that we then fed into a bioinformatics model. So the concept of this model was that a user would input a pre-designed set of primers and probes, and also the sequences that they wanted to see if the PCR and primers and probes were going to detect. The program then scans along these genomes for the best binding position, and then reports whether it's likely to detect the sample, and also if there is a mismatch, how this mismatch is going to affect the PCR. And we think it's really important to provide this quantitative data, because if you're looking at epithelial samples, for example, you can deal with more mismatches because you don't need you've got a very high CT, low CT, so it doesn't matter if there's more mismatches. Whereas if you're looking at Probang, for example, which has a very high CT, you can't really deal with any mismatches. So we wanted it to contain this information for the user. The next thing we needed to do was to briefly test the model. So this is just initial testing using different mismatches that we found using NCBI. So these are naturally occurring mismatches that were found in the FMD genome around this region. So we again ordered these as artificial constructs and tested them in both PCRs. And we found that the model was actually able to predict how the PCR performed within plus or minus 2 CT, so within the same log. So this was really promising data. However, we still need to test the model using natural sequences, not just artificial constructs, and also using different areas of the foot and mouth genome. That's all right. So just to conclude, the model we've created enables us to predict the effects of primers and probes and the mismatches in silico without having to do a large amount of laboratory evaluation. And we can therefore quantitatively estimate how the PCR is going to perform. By rapidly screening, it enables the researcher to decide if they think the primer and probe set is good enough for their uses, and then when they actually required redesigning. However, the next step is to incorporate the RT stage, so that we use a one-step PCR generally, meaning the PCR primers and probes are also used in the RT stage. So it's going to be looking at the effects of how the reverse transcriptase deals with these mismatches, as well as the polymerase. So that's the next step. So yeah, I'd just like to thank all of my colleagues at Pirbright and also Glasgow, and also EuFMD for letting me talk today.
That was very clear, Emma, and I think it can be very useful. So, are there any questions? Yes, Kees?
Well, quite. Yeah? Very nice talk. I have quite a practical question. Coming from the fields and working in several places diagnostically. Often you don't know, of course, the concentration in a sample, but you might already have an indication, because there is a big difference between the result of a pan-FMD PCR and a serotype-specific PCR.
Yeah.
Could you use that as a sort of, when you know what would be the difference, because the serotype-specific PCRs can be a bit less sensitive, but if you take that into account, that normally with a perfect match you would have 2 CT higher for a serotype specific as compared to the pan-FMD.
Yeah.
Can you use that as a sort of indicator for the probability that there are mismatches? When you would have a much higher difference, like your serotype specific PCR is higher.
Yeah. So
could you use let's say the ratio between serotype specific PCR and pan-FMD PCR in your model?
So yeah, I appreciate at the minute it is just a model based on the pan-specific assay. I am hoping to test the serotype-specific data with the model. And then if it doesn't fit properly, maybe, yeah, we do need to add some sort of ratio in, or alternatively, if you know how your PCR performs, have some way of inputting the likely CT for a good sample. But yeah, it's going to definitely need to recheck the model on how it works with a PCR. But that is basically why we've provided change in CT as opposed to the likely CT. So the initial plan was to provide the CT that your PCR reaction was likely to give, but because of the amount of variation between the pan-specific and the serotype-specific, we were concerned that it'd be impossible to predict, basically. So we thought by providing a model that would show how the PCR was influenced by the mismatches, it might be a more relevant number for more assays as opposed to just making it specific for a certain assay, if that makes sense. I'll talk to you later.
Okay, thank you very much. Very quickly, Dan, because we have to change gear. Yeah.
It's all right, Emma, you don't need to worry. It's not a question. It's more to remind people that this is not a trivial matter. In 2001, when we were using PCR, not as our necessarily frontline test, but real-time PCR was being used as a confirmatory test in that circumstances, we had a situation where even in the face of the outbreak, the virus mutated and the PCR failed to detect virus on some of the farms. So it's something that is a problem with PCR, and I think this is an approach that helps tackle that problem, or at least understand the extent of that problem.
Okay, thanks a lot, and thanks, Emma.
Thank you.
And now we have to move on because we have to change gear. I'm going very fast now to the poster presentation, so Aldo.